This particular math puzzle or math equation was very difficult for me to solve. I tried it a couple of times. I'd work on it for an hour or two, try again a few days later, try again a few weeks later. I never could solve it. So I just put it on the back burner and did some videos on some other ideas I had. So I ran out of ideas, so I just came back to this one and I solved it. I've got like 10 pages here, but I actually tested it with some different methods and came up with the same answer. So yeah, it's a little complicated, but I solved it. And here's what it is. I was curious about the velocity of a fluid rise in a cone. You can imagine if you're filling up a cone and as that water rises, say it's an upside down cone, as that water level rises, the velocity of that water rise continues to slow as the cone gets wider. All right, so I'm gonna go through some basic stuff, some basic proofs. This is stuff I figured out along the way. That's why I do this whole thing. That's why I do these videos and I try to learn this stuff. And I figure there's other math nerds that'll be curious, so I post this stuff. But I'll start out here with some things I didn't know, but I learned when I started looking into this. Let's just take a big, I don't know, rectangle box, I guess you call it. We got the area, 1 square meter. The height is 3 meters. You take your height times your area to get your volume. Height would be meters, area would be meters squared. Multiply them and you'll get meters cubed. Let's just say we have a flow of 3 cubic meters per minute. Notice the first clue here. The flow is 3 cubic meters per minute. Our box is 3 cubic meters because it's height times area, so 3 meters times 1 square meter. If flow is 3 cubic meters per minute and our box is 3 cubic meters, that means it will take 1 minute to fill. That was the first clue. The next clue is now we can easily get the velocity that water would rise up that box. The water level has to travel 3 meters and it'll do so in 1 minute. So the velocity is 3 meters per minute. And the formula for this actually is flow divided by area equals the velocity of your fluid rise. And that's assuming you're doing this on a planet with gravity, because if you're up in outer space and that fluid just comes out in a great big blob. So if we have gravity and that water is rising and you want to measure that velocity, it's just the flow rate, like such as 3 cubic meters per minute, divide that by the area, and I'll show a couple examples. This video is like a lot of my other videos that are kind of long. Every clue leads to another clue. So it's like a breadcrumb trail or a scavenger hunt. And then in the end, I get my answer. So that's what you're going to see here. It's just a series of clues and one led to the other. Now I'm going to show the math of the velocity of this fluid rise. Flow over area, 3 cubic meters per minute divided by meters squared. Bring up your meters squared here to a separate fraction and it's in the denominator. This meters squared right here, that's my first error. Meter cubed right here is the flow rate divided by meters squared. This turns out to just be meters. So you got 3 meters per minute. And notice that is a velocity, it's a distance over time. You could also say this is height over time because it's the traveling up the height, so that's the length or the distance. Notice that velocity of 3 meters per minute. You could say that's pretty fast compared to what I'm going to show next. Take this exact same box, turn it over on its side. So now you got your 3 meters on the bottom here. The area is now 3 times 1, so you have 3 square meters instead of 1 square meter. Plug the numbers into the same equation right here. Bring this up to a denominator, this 3 meters squared right here. You got meters cubed divided by meters squared. That's just meters. 3 divided by 3 is 1. Now we have a much slower velocity of 1 meter per minute. So it's the same box, but since we flipped it over, the velocity rise is now slower, but the box will still fill in the same amount of time. Next page. Next up, we have a cone here. Velocity will equal the flow rate. I keep wanting to say force, but flow rate over area. And if it's a circle, the area will be pi r squared. So in other words, next time when you're out somewhere in the backyard and you're pouring or dumping a hose full of water into a cone, and you're wondering how fast that fluid is rising in that cone, you simply take the flow rate of your hose, divide that by the particular area wherever that water level is, and that will give you the velocity of that fluid rise at that particular instant in time. I've actually done that just because I'm a math nerd. I'll take a beaker or something with the hose out back, or I did it in the shower also, and I filled it up with water to see what the flow rate was, so I could calculate roughly just how much water I used when I took a shower or something. What can I say? It was a slow day. But I did have to use that for filling the hot tub, because when you put the hose in the hot tub, you need to have some idea when to come back to check on it. And I knew the volume of the hot tub, then I found out the flow rate of the hose, and I knew when to come back, set my alarm. It took like 3 hours or something. It was a big hot tub. Anyways, right here I got some concepts: time versus velocity in a cone. So that's the velocity of the fluid rise. As time passes, as time increases, the volume that you're dumping in this cone is going to increase. The area is also going to increase. The velocity is going to decrease. Let's simplify some numbers here for the math and the equations I'm going to show. Let's say that time equals the volume, which is 1. So time, for example, at 1 second, the volume will be 1 cubic meter, and that's because we can do a flow rate of 1 cubic meter per second. So with that constant flow rate of 1 cubic meter per second, that means at 1 second we have 1 cubic meter. At 5 seconds we have 5 cubic meters. That way the numbers will match. But you don't have to make them match. You can plug in whatever ratio you want to. You can make this 3 to 1 or whatever. But the important thing is you have to establish some sort of relationship between volume and time. And I'll show that on the next page. All right, starting out, volume of a cone, pi r squared times height over 3. You could also say 1/3 pi r squared times height. But we got 3 variables here. We have radius, we have height, and we have volume. Let's turn this into just 2 variables. I'll decide that my radius will also equal my height. It'll be a 1-to-1 ratio. So 3 variables to 2 variables. Radius equals height. So this becomes, I guess I should explain how I can do that. Here's the radius right here of your cone. This dotted line right here, or dashed line, that's the outside of your cone. Here's the height, here's your radius. The cone is at a 45-degree angle. And it doesn't have to be 1-to-1. You could use whatever ratio you want to, 3.72 to 5 or whatever. So let's see here. Down here, then I have volume equals pi r squared times r, but since what I did is just turned h into r, so now I have r cubed right here. Volume equals 1/3 pi r cubed, and that'll be the volume of my cone. And the reason I have to get volume is the longer that hose is running in that cone, the higher that volume is. So that volume is going to be inversely proportional to the velocity of the fluid rise. Again, this is something that everybody needs to know every day, I imagine. So what we got here is I need to isolate my radius. So this becomes 3 times volume divided by pi. Take the cube root right there, and that will equal radius, which also equals height, because radius and height are equal to each other because I decided that my cone will be at a 45-degree angle. What I have to do here is turn volume into time, which I just did that when I said that the flow rate was 1 cubic meter per second or whatever. And then I turned height into radius when I decided they were equal to each other. And then I'm going to turn radius into area. That's why I had to get my radius right here. I'm going to turn that into area. And then I'm going to turn that into the velocity of the fluid rise, because the velocity of the fluid rise is equal to the flow rate over the area. So that's why I have to get that area. Next page. Okay, area equals pi r squared. What I'm going to do now is I'm going to do some nesting. And this whole radius right here of 3 times volume over pi to the 1/3, I'm going to nest this inside of the area equation. So this right here goes right there. And also, since this is to the 1/3, but then I have to square it because it's radius squared, so 1/3 times 2 equals 2/3. So I've turned radius into volume and nested that into the area of a circle. What I'm going to do now is do some simplification. This pi to the 2/3, pull that out and put it underneath that pi right there. Then I've got 3 times volume to the 2/3 power. By the way, it's a little tricky to remember. On my V's, I have to write VOL for volume and then VEL for velocity, so I don't get those confused. Okay, so pi to the 3/3 minus pi to the 2/3, and you'll get pi to the 1/3 times 3 to the 2/3 times volume to the 2/3. I just distributed that exponent through the parentheses there. This equation again, flow over area equals velocity, and this is all my area right here. So I take the flow, divide it by all of that to get my velocity. I'm going to simplify and just turn this into a C for a constant. So I got constant times volume to the 2/3 power will equal the velocity of the fluid rise. Graph it out and it'll look like this. I just take constant times velocity to the negative 2/3 for the y-axis, and then the x-axis will be time, which again also equals volume because I decided that we're running at 1 cubic meter per second. So those will be equal. And next page. To continue this line of thought further, just to see what I can do with it, this graph right here, let's take the derivative of this equation right here so we can find out the slope of that line. The slope, which is lowercase m, equals your constant times the derivative of the volume to the 2/3, because that is this part right there. So I take that 2/3 of my volume, bring it down. Actually, it's negative 2/3. And negative 2/3 minus 1 is the same thing as negative 2/3 minus 3/3. You end up with negative 5/3 as the exponent to your volume times negative 2/3 times the constant. Testing the slope there would be a little bit tricky, so it'll be easier to test the integral, so I'll do that. Let's just have a box here. Velocity stays the same. So say velocity of the water flow is the same because we're just filling up a square box. Velocity can be 3, the time could be 4 seconds. Distance over time equals velocity. That means velocity times time equals your distance. We can get the area under this line here by taking our velocity times time. 3 times 4 equals 12, and that is the distance that we will have traveled, or the height that the water level will have went up. I use this simple example here just to illustrate what I'm doing, because at first I was thinking if I took the area under the curve or the area under the line, that would give me volume. But by doing this, I realized I'm actually getting the distance or the height that the water level goes up. So yeah, I just learned this stuff and then I make a video. So now I'm going to test my equation to see if it works. We got our flow rate right here. We have the time, we have the volume. Simply because if we're flowing at 1 cubic meter per minute and we flow for 4 minutes, that means we will have a volume of 4 cubic meters. So I'm doing this the easy way here first, and then I'm going to do it with an integral. I said the easy way, I guess the, non-calculus way. So volume equals this whole thing right here of a cone, pi r squared times h over 3. Let's make the radius and the height equal each other again. We're back to what I already showed, pi r cubed over 3 equals volume. But now we know our volume is 4 because I just said that right up here, 4 cubic meters. So we solve for radius, and that will equal 1.56. That is the radius of our cone, and that is also the height of the water level because radius and height are equal, so that is 1.56. That's the non-calculus way, and I'm doing this to test my equation to make sure everything worked out. Now I'm going to do the calculus way. I'm going to take an integral here. By the way, I've done videos on integrals and derivatives on how to do them, so anybody can see those videos if they want. They're super easy. You just bring down your exponent, more or less. Okay, so the constant times our volume to the negative 2/3 power equals our velocity. That was our standard equation. Let's take the integral of volume right there. To take an integral, all you do is add 1 to the exponent. Negative 2/3 plus 3/3 equals positive 1/3. Actually, I got that right here. Negative 2/3 plus 3/3 equals positive 1/3. I actually don't know what these notes say because I just scribble them down really fast and then make a video. So what we end up with is our constant. Actually, what I have to do now is take this 1/3 exponent, invert it, and bring it down. So it becomes 1 over 1/3 right there times the constant, and it goes from A to B. So right here is the integral to test my equation to see if it works. And I think the reason I'm a little extra happy right now is because I didn't get the same result with this, with the calculus, compared to when I did it without calculus. I got 2 different answers, and I noticed the non-calculus way gave me an answer that was 3 times greater. And so I just thought I really flew off the rails and had no idea what I was doing. And then I realized what I did here is I didn't take the inverse of this 1/3 when I brought it down. So that 3 right there was where I messed up. Okay, next page. I was just saying all that because, yeah, I put a lot of work into trying to figure this out, and after like 2 hours of work of figuring it out, nothing worked right, and it turned out to be just a simple arithmetic error. So I was pretty happy to when I realized everything worked out. Okay, let's take our constant, turn that back into our numbers here. Flow rate, which will just be 1 divided by pi to the 1/3 divided by 3 to the 2/3 times volume to the negative 2/3 equals velocity. Let's use our integral now. So all of this times 3 times velocity to the 1/3. We're going to go from 4 to 0 because we are at 4 seconds. And plug in your numbers, you get 1.56, the same as before. So what this does, this elusive problem that took me forever to figure out and many, many pages to explain it, this relates time to the velocity of the water level as something is filling up. So you can say at 5 minutes or at 2 hours, the velocity in that cone will be such and such. Also, my general philosophy on why I learn this stuff and make these videos, especially this video in particular, I will never use this, and I can't imagine anybody ever needing to use this. So for me, this is just like running on a treadmill. You may not go anywhere, but you're a lot better off for doing it. And this brain workout I had with this particular problem here reminds me of my days at the gym when I'd go have such a hard workout, like on leg day or something. After 2 hours, I could barely walk when I left, but I felt great. So that's kind of what this problem did for me, except in a mental way.